Okay, so you want to escape a black hole. Here is the problem. The version of black holes most people carry in their heads is wrong. Not slightly wrong, completely wrong. Because what physics textbooks describe at the introductory level, the clean boundary, the point of no return, the simple death sentence for anything that crosses it, bears little resemblance to what the interior structure of a black hole actually looks like when you work through the full mathematics. Most people's grasp of black hole physics fractures precisely at this divergence between the two conceptions. Before any discussion of escape makes sense, you need to understand what a black hole actually is in structural terms, because black hole is not one thing. It is at minimum four distinct regions, each governed by different physics, each presenting different constraints on what matter and energy can do. The first region is the exterior. This is normal space. Gravity here follows the same inverse square law it follows everywhere else in the universe. At a distance of 1 light-year from a stellar mass black hole of 10 solar masses, you would feel gravitational attraction indistinguishable from standing 1 light-year from any other 10 solar mass star. The second region is the photon sphere. For a non-rotating black hole described by the Schwarzschild metric, this boundary sits at 1.5 times the Schwarzschild radius. At this distance, photons traveling tangentially to the black hole travel in closed circular orbits. Light can literally circle the object indefinitely at this radius. You can still escape from here. A spacecraft at the photon sphere with sufficient thrust pointing directly away from the singularity can still reach escape velocity and return to open space. The third region is the ergosphere, and this one only exists around rotating black holes, which astrophysicists now believe describes essentially every black hole that forms through stellar collapse. A rotating black hole is described by the Kerr metric rather than the Schwarzschild metric, and the Kerr geometry produces something the non-rotating case does not: frame dragging. The rotation of the black hole physically drags spacetime itself around with it, the way a spinning ball drags the air surrounding it, except what is being dragged here is the fabric of space. Inside the ergosphere, which extends beyond the event horizon and bulges out toward the equator, no object can remain stationary relative to distant observers. The rotation of space-time forces everything inside it to co-rotate. But escape from the ergosphere is still mathematically permitted. The ergosphere is not the horizon. The event horizon is where the physics shifts from difficult to absolute. For a non-rotating black hole of 10 solar masses, the Schwarzschild radius, meaning the radius of the event horizon, sits at approximately 29.5 kilometers. For a supermassive black hole like M87, which carries a mass of 6.5 billion solar masses, the event horizon extends to roughly 20 billion kilometers, larger than our entire solar system. At the event horizon itself, escape velocity equals exactly the speed of light. Inside it, escape velocity exceeds the speed of light. Since nothing with mass can reach the speed of light, and nothing can exceed it, the interior is causally disconnected from the exterior universe. Every future directed path inside the event horizon terminates at the singularity. This is not a statement about technology. It is a statement about the geometry of spacetime. The fourth region is the interior itself, between the horizon and the singularity. In the Kerr solution for rotating black holes, this interior is more complex than the simple Schwarzschild interior. The Kerr metric describes not one but two horizons, an outer event horizon and an inner Cauchy horizon. Between them sits a region where the mathematics permits, at least formally, trajectories that avoid the central ring singularity entirely. Theoretically, an infalling observer in a Kerr black hole might pass through the inner horizon, survive the singularity by threading through the ring, and emerge into a different region of space-time. Whether this is physically realized or whether quantum effects destroy the inner horizon before any observer could reach it remains one of the genuinely unresolved questions in theoretical physics. So the question of escaping a black hole depends entirely on which region you are in when you ask it. From outside the photon sphere, escape requires nothing extraordinary. From within the photon sphere, but outside the event horizon, escape requires enormous energy expenditure directed precisely away from the singularity. The closer you are to the event horizon, the more extreme the required thrust. At a distance of 1.001 Schwarzschild radii from a 10 solar mass black hole, a spacecraft would need to sustain an acceleration of approximately 10 to the power of 13 meters per second squared, just to remain stationary. No known material can withstand tidal forces at that proximity, and no known propulsion system produces thrust at that magnitude. Inside the event horizon, classical general relativity is unambiguous. There is no path outward. Every direction in space points toward the singularity. Hawking radiation changes the accounting, but not in the way most people think. In 1974, Stephen Hawking demonstrated using semi-classical methods, meaning quantum field theory applied to curved space-time without a full theory of quantum gravity, that black holes are not perfectly black. They radiate thermally. The mechanism involves virtual particle pairs forming at the event horizon, with one particle falling inward and one escaping outward as real radiation. The temperature of this radiation for a stellar mass black hole of 10 solar masses is approximately 6 times 10 to the negative 9 Kelvin. That is 6 billionths of a degree above absolute zero. It is far colder than the cosmic microwave background, which sits at 2.7 Kelvin. For stellar mass black holes, Hawking radiation is physically irrelevant at present, because the incoming cosmic background radiation delivers more energy than the black hole emits. The evaporation timescale for a 10 solar mass black hole through Hawking radiation is approximately 2 times 10 to the power of 74 years. The current age of the universe is 1.38 times 10 to the power of 10 years. For primordial black holes, hypothetical objects formed in the early universe with masses far below stellar mass, Hawking radiation matters. A black hole with a mass of roughly 10 to the 11 kilograms, about the mass of a large mountain, would be evaporating at detectable rates right now. A black hole small enough to have formed with the mass of a large asteroid would have already evaporated entirely. The final stages of evaporation are explosive. In the last second of a black hole's life through Hawking evaporation, it releases energy equivalent to roughly 10 to the 23rd joules, comparable to millions of nuclear warheads. But this process represents the black hole losing mass until it no longer exists. It is not escape in the conventional sense. The information that fell into the black hole, the atoms, the particles, the structure, does not come back out intact in any form that preserves original configuration. This is the information paradox, and it remains unsolved. There is one proposed mechanism that gets closer to something resembling extraction rather than evaporation. The Penrose process applies specifically to rotating Kerr black holes and specifically to the ergosphere, not the interior. An object falling into the ergosphere can, under the right conditions, split into two pieces. One piece falls inward with negative energy relative to a distant observer. The other piece escapes outward with more energy than the original infalling object carried. The black hole loses mass and angular momentum. The escaping fragment gains energy at the expense of the black hole's rotation. The theoretical maximum efficiency of energy extraction through the Penrose process is 20.7% of the infalling mass energy for a maximally rotating black hole. Astrophysicists believe relativistic jets, the massive plasma structures extending thousands of light-years from active galactic nuclei, may be partially powered by a magnetohydrodynamic version of this process called the Blandford-Znajek mechanism. The firewall paradox, proposed in 2012 by Almheri, Merolf, Polchinski, and Sully, adds another layer of complication to the interior picture. Their argument holds that if Hawking radiation is truly information-preserving, as quantum mechanics requires, then the event horizon cannot be a smooth, locally unremarkable surface for an infalling observer. Instead, the horizon must be a wall of high-energy radiation that would destroy any infalling observer instantly. If the firewall is real, the interior of the black hole is not the quiet, locally flat region that general relativity predicts. This directly contradicts what the equivalence principle of general relativity implies. Resolving this contradiction is one of the central unsolved problems in theoretical physics, and it matters for the question of escape, because it changes what the interior actually is. The honest answer to escaping a black hole runs through three separate conclusions depending on where you start. From outside the event horizon, escape is always possible and becomes progressively more energy-intensive as you approach the horizon. From inside the event horizon, within classical general relativity, escape is geometrically forbidden regardless of technology or energy. The structure of space-time itself closes every outward path. The only classical exits are the mathematically permitted trajectories through the Kerr interior, which require passing through regions where the physics becomes singular, and where quantum gravitational effects almost certainly dominate in ways the current theory cannot describe. Hawking radiation offers a kind of dissolution rather than escape. The Penrose process offers energy extraction from the ergosphere, not from the interior. And the firewall hypothesis suggests the interior may not exist in the way the equations imply.